Mm.
Hey, here we go.
Hi, everybody. Sorry for the delay. There was some technical problem and also misunderstanding. And thank you for hanging there and to wait for us. So I'm Anarita Marrano. I'm a postdoc at UMass Boston, but also I just recently started a new position for Ag Biodata, a consortium of database in agriculture. And here we have
Felipe
Philip.
Matias. I'm using my phone. Guys, you have no idea how how fun is organizing these workshops. There is a lot of challenges that just show up and then we need to figure out. It's quite fun, right, Ana and
Yes,
Rita?
a lot of
So
emotions. Every day,
yeah,
every time, a lot of emotions.
and I'm talking here from Brazil today. It's amazing temperature. I have many birds around here from a small town called Tupaciguara at the state of Minas Gerais. It's very tiny, teeny, but it's very cute to organize it. You should come to visit us sometimes. Well, we always start our workshops with a presentation. Do you want to show the
Sure.
presentation?
Yeah,
Here we
sure.
go. Perfect.
So yes, guys, we are at our third workshop series. This time it's about principal protocols and pipeline for drone phenotyping. But before starting, we want to remind you who we are, and especially for the people that just join us for the first time. We are PhenomeForce. We are a platform of people working in phenomics. So as a platform, we try to bring together as much as we can all people that works with plant phenotypes. So all the key stakeholders and everybody. And so our main goal is first of all connecting these people. Also, we want to empower early career researchers. So this is why many times you see postdoc or graduate students presenting their pipeline. And as you see, so why we empower researchers working in phenomics by providing free training, and so free online workshop. And as you can see, these workshops, they are permanently at our YouTube channel, which is a library of resource that you can use anytime you want. So me and Felipe, we started this platform in 2020, and lately we also have been joined by Claire, but as we just want to say that we are looking for collaborators. So if you are very interested in working with us and let's say helping us organizing the future workshop, please contact us and we will be very happy to talk with you. Um,
Perfect. Yeah, this season we have a partnership with a group called Drawn to Phenom. Is a new group that just started to work with empowering high throughput phenotyping using UAVs. And it's a big group. Actually, we have a partnership with some colleagues from other institutions, Max Feldman, Dave LeBauer, Jennifer from Montana, Dr. Adriana Silva from Brazil. So this community, the main intention is to apply a survey and to understand how UAV has been using on research, on plant breeding, and all the other majors. And with this information, we also want to give feedback for our community, what's going on, and also developing pipelines to use UAVs in all steps, right? And then that's why we decided to make this workshop series related with UAVs.
and so, yeah, so we are at our sixth workshop. So today we have Ce Yang from University of Minnesota and Tyler Nigon from Sentera. And they are going to talk about an automated approach for spatial cropping and plot identification using hyperspectral area imagery. And so with that, we want to welcome them on the screen. So hi guys.
Hey, welcome.
Hello.
Hi.
Thank you for accepting to present. I'm gonna if you um, so I don't know if I will share your screen.
Yeah, it's already here. Let me share.
Mhm.
Here we go.
Mhm.
Perfect. So guys, we're gonna be right here. Let me know if you need anything. And for you over there, if you have questions, just type in the comments. Anahita and I will be here to give the support and make the questions. Okay?
Yeah, and
Enjoy.
enjoy, guys.
Okay, should I start now?
Yes.
Okay. Hi, everyone. I'm Ce Yang from the University of Minnesota. I'm currently an assistant professor leading the Ag Robotics lab. And my research focus is drone remote sensing for precision agriculture and high throughput phenotyping. And today I'm going to present with my student Tyler Nigon, who graduated in the past summer and successfully sold his startup company to a Minnesota-based, fast-growing ag tech company, Sentera. And now he's working for Sentera. I'm very proud, by the way. And the topic of today's talk is an automated approach for spatial cropping and plot identification of hyperspectral aerial imagery used in small plots and on-farm research. So the outline of this 1 hour, 1.5 hour long talk include introduction, which is drone remote sensing for addressing agricultural issues, and the 4 parts. Here, part 1 and to part 3, we will talk around a Python tool that Tyler developed during his PhD program called HS Process. And also we have a bonus part 4, which is another Python package, which is called EONR. The full name is Economic Optimum Nitrogen Rate. And in the end, Tyler will give some conclusion marks. So introduction, can we go to the next slide? So our focus is using drone remote sensing for addressing agricultural issues. So we will next. I'm going to talk about some very general agricultural issues that we face, and the specific issue with over application of fertilizer, especially on the in the Corn Belt area. And then I will give very brief introduction of hyperspectral imaging, and this leads to a case study in aerial hyperspectral imagery to predict early season nitrogen uptake. So some general agricultural issues we face in our world. First, foremost, which is the increasing world population. We are expecting to see 9.7 billion, over 9.7 billion people by 2050. So food security is a very important issue. We need to feed all the population. To increase or guarantee the best yield for staple crop production, usually over application of fertilizer is a practice for growers, especially in growing corn. But this caused negative impact to our environment, which is pretty well known, and also it contributed to the climate change. And also, growers are facing high labor cost and the labor shortage from year to year. Now it's a more severe problem. So most of these agricultural issues are closely tied to the nitrogen cycle, which apparently have impact from ground all the way to of our atmosphere. So including feeding the increasing population, over application of fertilizer, nitrogen fertilizer, and the negative impact to the environment because of the excessive nitrogen use, fertilizer use, which have this impact to climate change and food security, which is the food security problem we are facing is to feed the increasing population. So the corn nitrogen use, in fact, does not peak until after late July. If we look closely into this graph here, the blue curve is the annual rainfall pattern, and we can see that it doesn't. It peaks in about July, the starting of July, or the end of June. But the leaching potential happens before this time because of the spring snow melt and early summer irrigation, early summer rainfall. And we can see a peak of nitrogen leaching potential around June, which is in fact the early growth stage of corn. But the corn nitrogen use during the nitrogen leaching peak in June is in fact still very low, which means that we can delay the timing of nitrogen fertilizer to reduce the likelihood of nitrogen loss through nitrogen leaching. I cannot hear you, Tyler. Do you want to add something? Tyler is more
Can you hear me now?
in this area. Yeah.
Yes, I just want to add one final point to this. So delaying the timing of our nitrogen fertilizer application gives us this opportunity to do remote sensing and get the nitrogen status of the crop, to use that information to make a recommendation on the exact timing and the rate of the fertilizer. And so that's really the overview for why we're using remote sensing for this use case.
Thank you for adding that. So a little bit introduction of hyperspectral imaging. I believe many of you in the audience are already familiar with hyperspectral imaging, but for those who are new to this technology, I would like to have a very brief explanation. So here on the left side, we see is a typical drone hyperspectral imaging or airborne hyperspectral imaging scenario. If you think about a color image taken either from a drone or airplane or just from our handheld device like a smartphone, what we get is a picture or image that contain millions of pixels. And per pixel, we have three values, in fact, the red, green, and the blue, which form all the different colors that we see. And in the spectrum, the red, green, and blue bands each cover about 100 nanometer, which is a pretty wide range or wide bandwidth. And we only have three values. But in hyperspectral images, we still get a lot of pixels, but per pixel, we get hundreds of values that cover the range of not only visible, which is the red, green, blue, but also part of the near infrared. And also, the hyperspectral image cut the spectral range into hundreds of narrow bands, which give us those hundreds of values. And if we plot information from one pixel, we in fact get a spectral curve. And as you can see showing here, we can see very different spectral curve from vegetation to soil or water. So they all have different spectral curves. And from our research and also from literature, we are confident to say that hyperspectral imaging can tell way more information than color imaging or some other technologies. That's why we can use this in our case for the nitrogen uptake study. And a real hyperspectral camera looks like this on the right side of this slide. On the top, you can see a hyperspectral camera, which contains three parts. In the front is the lens, and in the middle is a spectrometer, and in the end is a CCD camera, which has the sensor to sense the different bands. If we look at the procedure, in the middle of the right figure, you can see the lens or the optics will receive reflectance light from an object. In our case, it can be a crop or a plant, and the reflectance light will go through the spectrometer, which basically cut the light into hundreds of bands, and each of the bands will contain only 2 nanometer information in the form of photons. And the sensor in the back in the CCD camera will sense these spectral bands and record the the strength of the light in each of the band, and that will eventually give us the hyperspectral image for the whole view. So we will use a case study to start today's technical details, which is the aerial hyperspectral imagery to predict early season corn nitrogen uptake. I believe we already gave enough background information for conducting such a study, the necessity of this. And Tyler, if you think you need to give some makeup information, please go ahead. And now I would like to hand it over to Tyler.
Okay, thank you for the introduction, C. Yeah, so just finishing up on this introduction for the use case before we get into the technical details of the image processing and everything, just wanted to just make clear what our overarching research goals are, and that is looking at nitrogen fertilizer recommendations and improving our ability to make them, both from producer and non-producer perspective. So from a producer, they're looking to maximize their profits so they can run their business. And then there's this other perspective from other stakeholders related to the environment. So we want to be responsible and minimize nitrogen loss to the environment. And so with this, you know, a lot of this is based on my dissertation that I completed in C's lab. There were two main research topics, and that is the first being taking an accurate inventory of in-season crop nitrogen uptake, and this is where we use hyperspectral remote sensing. There was another topic of calculating the economic optimum nitrogen rate, quantifying uncertainties, and quantifying externalities to the system to help get a better understanding of this nitrogen challenge that we face. So with that, I have this broken up into 4 parts, and the first part, I'm just going to give an overview of our hyperspectral image processing protocol that we used in our lab for this experiment. Now C just kind of gave a lot of background on this, but with high resolution aerial hyperspectral imagery, we have this issue, or it's an opportunity really, to have pixels that are pure soil, have other pixels that are more or less pure vegetation. And so we can have this ability in one image to really segment out and decipher the differences. And I'm not going to get into the spectral response. I think C covered that, but you know, we see different signatures for different targets, and that's indicative of the target. And when it comes to vegetation, you know, the deciphering between a stressed leaf or a stressed plant and a healthy leaf and a healthy plant. So I think we drove this home already. Our goal is to predict early season nitrogen uptake using high resolution aerial hyperspectral imagery. This is just a little diagram kind of outlining the whole process. Step 1, capture the data. 2, process all of the imagery. That can be a very tedious task. Once we have that in a place where we can plug that into a machine learning model, we use supervised regression models to calculate or predict, train a model for predicting nitrogen uptake in early season corn. So we do that training and tuning process, and then finally the prediction process. So I'll walk through at least steps 1 and 2 here, and I'll show a little bit of the results later on in this webinar. So step 1, capturing the imagery. We used a DJI Matrice 600 Pro, and we had on in, what was it, 2017, I just want to make a comment to that. When we started this research in 2015, this drone wasn't available yet, and we were using a different drone that I don't know, was more or less built in a garage, I guess, but it satisfied our purpose for holding, or like being able to carry the payload of our heavy hyperspectral camera, the flight computer, you know, all of the different components that are necessary for hyperspectral imaging. And we didn't really get any data for the first 2 years. It was really, really frustrating. And then once we got this drone, things kind of turned around for us because it just worked better. And I'll also note that, you know, before we got the Matrice 600, the old drone worked fine by itself. The hyperspectral camera worked fine by itself, but this integration and getting them both to work together was very difficult. So you see up in the little subset image on the right, that's the flight computer on the left, the camera itself. And so we use a Resonon Pica 2 is positioned right next to it. And then there's the little red box here, that's the inertial momentum unit connected into a GPS receiver. So this whole system, this flight system, is completely independent of the drone itself. So we had to program the computer, the camera system for capturing imagery the way we needed it captured, and then we had to program the drone independently to fly over our area of interest, lining up the speed, the frame rate of the camera, the altitude, our desired specifications that we wanted to see in our final imagery. So this camera, is sensitive to 400 to 900 nanometer spectral range, spectral resolution of around 2 nanometers. There are 240 spectral channels. Each the spatial imaging array was 1 by 640, so it's a line scanning camera, bit depth of 12 and 33 degree field of view. This is a map, an overview of one of the experimental sites. I guess there's 2 experiments here. So the Waseca small plot, we called it, and then the Waseca whole field experiment. And then we also had another experiment in Wells, Minnesota. But the reason I show this is just that, we had 3 experiments. I think this is very common where we run into an issue where, okay, because of the different scale of the experiments, and focus over on the cropped plot size over here. Wells is a small plot trial, and we're dealing with plots that are 6.2 meters by 1.8 meters. Our Waseca small plot experiment, it's called small plot relative to the whole field, but these are plots that are about 100 feet long by about 30 or 40 feet wide. And so we are just working at a different scale. And then on the other extreme, the whole field, we flew the drone over this whole 35-acre field. And, our plot size where we're collecting the samples from is 10 meters by 10 meters. And so we have a different flying altitude to cover the extent of the experimental area, which means that we have a different pixel size for each study. And so this can provide challenges when we're trying to train a model and cross-validate and make the best predictions we can. But it's absolutely, real world scenario. Like, we can't expect to have all exactly consistent imagery in the real world. Everybody kind of, we have to adjust these specifications, our flying height and such to make it work, I guess. Because of battery life and things like that. So, I have a table here just kind of outlining for each of the experiments, the data sets that we collected, how many observations we had, the growth stage, sampling dates, and everything like that. I'll just kind of give an overview here. So there's 6 data sets over 2 years, 3 experiments in total. 247 observations. So when I say observations, this is how many ground truth samples that we measured. So we collected early season corn nitrogen uptake. So that included both the whole plant sampling and then drying it, sending it into the lab for the wet chemistry analysis for nitrogen concentration. The data set covered 4 growth stages in the early season, so V6 corn to V14 corn. The sampling, the ground truth sampling, was always within 2 days of image capture. We try to coincide that as close as possible. Image time was around solar noon. And we had different plot sizes, which I covered a little bit earlier. Okay, so that covered the image capture portion of it. Now on to the more interesting parts, let's say, the image processing. So this is a diagram I put together just to outline the whole image processing workflow, and just not looking at the details for now, just focusing on the high level. We have data collection, both from the image capture perspective as well as the ground truth tissue sampling. And then there's this in-between component, all this image processing that is just a hassle. And what I'm presenting on today, made this much less of a hassle in the end, and I hope it can be the same for other researchers. And then finally, over on the right, the last step is the analysis. As researchers, this is really what we're interested in. We want to take our ground truth data, we want to take our imagery, we want to skip past this step if possible and plug it into a statistical model, train the model to get some actual results. So, and I'll back up a little bit. So after we capture the imagery, there's a couple steps, conversion to radiance, and then doing the geo-rectification process using the onboard GPS, the IMU, to project each image onto the actual location that it is on the Earth. I'm not going to be going through these steps in this talk, but they were done. And then where I'm going to start here, the conversion to reflectance is what we did. We put out reference panels in the field every time we went and flew the drone, a black and a gray panel. These were a 50-50 mixture of gray paint or black paint and barium sulfate by weight. The barium sulfate is a powder that diffuses the light, so there's less likelihood of glare. It takes away about 95% of any glare that would happen from the direct beam of, or the direct exposure to sunlight into the sensor. So this gray panel, it was pretty flat in terms of reflectance across the wavelengths that we were considering, ranging from about 45% to 41%. So we used the empirical line method for performing the reflectance conversion. Okay, the next step, which I'm going to talk extensively about in part 2, and is really the meat of this webinar here, is cropping the imagery by the particular plot boundaries. And so just an introduction, I mean, I think it's pretty straightforward, but we have this larger hyperspectral image that oftentimes covers many plots, and we want to only consider the pixels that represent that are within the extent of a particular plot, as we would refer to it as. And the plot is usually just one experimental unit. Whatever scale we're collecting other information, other data on. And in our case was we're collecting plant samples for biomass and nitrogen concentration. The next step we did was the clipping, a spectral clipping. And so this is on the spectral domain. So looking at one single pixel and looking at its spectral response, there are certain bands that are very noisy. They have a really low signal to noise ratio. And so we would just remove them. So in the blue region, the oxygen absorption region and the water absorption region in the atmosphere, even though we were only capturing imagery at 20 to 80 meter altitude, we're still seeing a little bit of noise in these areas. So we just got rid of them. We still have plenty of data. We went from 240 bands down to 210 bands. Step 4 was a smoothing process. Also looking at a single pixel, looking in the spectral domain. We do see a lot of that up and down, that noise or scatter. So we just use a Savitsky-Golay smoothing algorithm to just smooth that out to have more consistency on a pixel by pixel basis. And then step 5 was segmentation. So after all of these steps were complete, then we still have an entire hyperspectral image, 210 spectral bands. And there are, getting back to my very first slide, we have vegetative we have pixels that are representing the corn plant, and then we have pixels that are representing soil. also have pixels representing shadow. And so do we want to consider all of those pixels when we start plugging this into our statistical model? In our case, no, we did not want to. And so we performed the segmentation step. And the goal here was just to remove any of the unwanted pixels. We wanted to keep any of the pixels that are most likely to be pure vegetation. So we wanted to get rid of any of the soil pixels, any of the shadow pixels, and then really pixels that were maybe mixed pixels, maybe part vegetation, part shadow, part soil. We wanted to get rid of those. So we used a spectral index called MCarry2.
Hi, Tyler.
Yeah.
Sorry to interrupt you. There is a question. Do you want to take it? So what gimbal model do you use? Do you need to adjust roll, pitch, yaw before fly? We use Gramsci H16. We have to manually adjust them, and the mosaic image has distortion along the edition path.
Yes. So what gimbal model do we use? The model is blanking me, but DJI only makes one gimbal for the Matrice 600, so you can look that up. C, do you know? There's all these different M names. Anyways, it's DJI's gimbal for their Matrice 600. Really a pretty good gimbal. Do you need to adjust roll, pitch, yaw before fly? So it is a self-calibrating gimbal that will level itself out. With that said, I often found that it was never perfect. So when I was out in the field, I always carried a little bubble level with me. And I put that, right before, like one of the last steps before I would take off to fly, put that bubble level on top of the camera. And I'm just going to back up to the slide.
Oh, I would put it on the...
So I put the bubble level right here on the camera. And then I had my little gimbal controller to just get that perfectly level, or as best as I could. Now the gimbal is nice because...
Sorry. So also a commentary, but the chair say in the chat, it's the model is Ronin MS.
Bingo. Yep, that's it. Sorry, I was just blanking me. But the gimbal is great. We set it up to follow the orientation of the drone, and so when the drone would change its heading, the gimbal would follow it. And when we started moving with the drone, you get a little bit of tilt like that, and the gimbal would correct so that the camera was always theoretically supposed to be pointing nadir direction, so straight down. And of course, there's always error in this, and so that's where the IMU comes in to be able to just measure those differences. And when we show some of the hyperspectral full data cubes, if I remember, I'll point out, kind of how that affects the imagery.
Okay, thank you so much.
Yeah, you're welcome. Yes, so and if there are other questions, please type them in and I'll address them right away when we're still on the topic. So the MCarry2 index, modified chlorophyll absorption ratio index 2, I think it is. Anyways, it is sensitive to leaf area index and is rather insensitive to chlorophyll influence. And so this was a good index for us to use in our use case because we're putting on different rates of nitrogen fertilizer. Nitrogen fertilizer rate directly correlates with the amount of chlorophyll in the plants. And so to have a fair comparison at this segmentation process, we wanted to use an index that wasn't biased towards, some plots had more chlorophyll, some plots had less chlorophyll. So it really worked out pretty good for us. And this image obviously shows the result of the MCarry2 segmentation. After we filtered out, looking at the histogram of this whole image, I don't know, there were probably 8,000 pixels or so. We filtered out all of the MCarry2 all the pixels that had an MCARE2 value below the 90th percentile. So we made this assumption that anything over the 90th percentile were most likely to be pure vegetation pixels. And then finally, we took what was left of these pixels that weren't masked and just took the mean reflectance spectra. And so we had 210 reflectance values corresponding to each of the 210 wavelengths that we had. And then that's what we would use for the machine learning, for the statistical models that we were building to try to predict nitrogen uptake. So I'm not going to get into the results of that right now. Instead, I'm going to go back to the image cropping step. And this, in particular, this Python library that I had developed called Hsprocess, which is an open source library for geospatial processing of aerial hyperspectral imaging. And so this is, there's a documentation page out there on the web, hsprocess.readthedocs.io. And this project is also hosted on GitHub. And so here's just kind of a screenshot of the website here with the link. So go ahead and check that out. And of particular attention for anybody that wants to follow along with most of the slides that I have here in the next, 40 minutes or so. I'll point you towards this link right here on the GitHub page. And this is just one of the Spatial Mod tutorial of Hsprocess. So it's going to be following that. It uses the same data sets. You can download the data that I'm working with and, come back to this later. And can we share that link as well?
Yeah, sure. I will share it on the chat.
So maybe it'll be more accessible to everybody. Okay, so in part 2 here, I'm going to focus on, like I said, Hsprocess, but I'm really going to, I'm not going to spend, really any time on the clipping, smoothing, and segment steps. With that said, Hsprocess, it does have tools to do each of these other steps. But, this is, in my opinion, the most challenging, the most subjective, and it has the most need for new tools to automate these processes. I already went through this, but yeah, Hsprocess, the idea is like we can batch process imagery to go all the way through to data analysis without having to spend the tedious efforts of doing the processing, which I'm sure many of you have experienced. Before I really get into the library, I just want to touch on some points, what was my motivation for development. And here I have listed out a few of the big ones. Number one, to streamline the processing steps required to perform hyperspectral data analysis. Although commercial software perhaps does exist for some of these needs, there's really open source software that is both flexible and streamlined did not really exist, especially, like I said, for this image cropping and plot identification step. In the last 3-4 years, I think now there's some other solutions out there, which is great. But that was one of the motivations. Another one, minimize time and effort required to perform image processing tasks. So I wanted to be able to batch process and just throw it at a computer and run in parallel processing and not have to worry about it. Number 3, minimize and potentially eliminate the number of steps where user intervention is required. And so this is where, if we can have this all done programmatically without having to do manual steps, we can get on with our research and do what we're really trying to do here as researchers. Number 4, yeah.
Tyler, there is another question. So a question on data processing and analysis strategy. Do you use resonance software, Spectrum Pro for data rectification, mosaicing, and reflectance generation, and then use Python for the analysis?
Yes, that is exactly right. I have this kind of clouded out, but in this whole image processing area, this area on the left here is, so the radiance conversion, the Geo-Rectification, and the Reflectance conversion are all done using Spectranon or Spectranon Pro. And then after that, I use HS process. And so this is, what I was referring to, like, could have I used Spectranon to do all of these steps? Yes, absolutely. It's all built in Python. And so I could have probably dug in and maybe made my own plugins to do what I needed to do. And I seriously considered that right from the get-go. But I thought, okay, if I can also just build a library that maybe can be used as a Spectranon plugin, that's maybe a more suitable way. I have not done that yet. But
okay, thank you.
As far as mosaicing, because that was one part of the question, I have not. I've not ever done mosaicing on the hyperspectral data sets that I've used for my research purposes. The reason being that mosaicing on those pixels that overlap, there's going to be some resampling that happens, and it's going to alter the pixel integrity. I made sure when flying over my plots that I had sufficient coverage where I was getting, like, for the most part, the full plot in every image, or I always had an image where I had the full plot in that same image. And so I never did that. It's also, I don't know, kind of a nightmare to deal with mosaic hyperspectral imagery when I have 4,600 megabyte images and I go to try to mosaic them together. It's like, okay, what am I going to do with what am I going to, 600. So what am I going to do with, like a 15 or 20 gigabyte image? It's got to be brought down in size at some point.
Okay.
So, everything I'm talking about is from, the imagery was from the original data cube, or at least the spatial extent of the original data cube. So no mosaicing.
Okay. Thank you, Tyler.
Yes, absolutely. Okay. A few more points on the motivation for development. I wanted to provide a framework for processing an entire hyperspectral data set that we could at least script out and repeat, even if it's like 1-2 years down the road and this data is going to be used for a different project. Like, I wanted to have a framework where there's a script where they might be able to change a few parameters to adjust the image processing protocol or methods to fit their use case that they're looking at, which, in my experience, like how we process these images, the rather subjective decisions that we make along the way, it all usually ties back to what is our goal, what is our research objective. And so this data will live on for a long time, at least I hope, and just kind of wanted to have a framework where that data could be processed in a different way very easily, especially after going through the first time. And with that, I think the last point, enable people to more easily document these complex processes and inherently subjective parameters used for processing this imagery. Things like segmentation thresholds, spatial plot buffers, which we'll get into in a bit. Okay, so HS process. There are 7 classes here, and I'll just kind of give an overview into the library here. So there's these utilities classes. Defaults, which it just contains default values for different settings. So, if a particular user wants to change their defaults, they just have to change it from here. And then all of the other classes then access the defaults when needed. HSIO is based on a very nice Python library called Spectral Python. HSIO is a class for reading and writing hyperspectral data files, as well as accessing and interpreting the metadata file along the way. So as we process an imagery, I always want to record the processing step that was done in the metadata. So there's always a trace back or a history on how this image was processed over time. And then HS tools, this is kind of like the utilities class, basic tools for manipulating the SPI files. That's what Spectral Python uses as its hyperspectral imaging object. So these are just image cubes, a SPI file. So just basic tools for manipulating the images and the metadata. The actual image manipulation classes, we have segment, which I think this should all be pretty self-explanatory, but this is a class for dealing with the segmentation and the masking of image data. We have Spatial Mod, which is I'm going to dig into deeper through the remainder of this part. Spatial Mod is a class for manipulating data within the spatial domain. So, for example, cropping a data cube by a geographical boundary. And Spec Mod is a class for manipulating data within the spectral domain, which is usually always pixel-based. So things like clipping out bands that have a low signal-to-noise ratio, clipping out or doing the smoothing across the spectrum. That's all in Spec Mod. And then there's a batch class. So for any of the segment, Spatial Mod, or Spec Mod, there's also batch functionality. So if I have a whole directory of files, I can call the batch to just process those all in the same way. There are other ways to deal with batch processing outside of the library, using some command line tools and bash, things like that, which is certainly doable. But there is this easy access to do this right within the library as well. So like I said, I'm going to focus on the Spatial Mod class. So Spatial Mod has two functions, crop single and crop mini GDF, it's called. And crop single crops a single plot from an image. And we'll get into that. We'll get into each of these in detail. Crop mini GDF, on the other hand, is when we have a hyperspectral image that has many plots within the image. The idea is this function then will crop all of those plots from that single image when comparing to a geodata frame, which might be a shapefile, a polygon of the plot boundaries.
Hi, Tyler. There is a question for you.
Yes.
Can you share a bit more information on spectral data calibration? Will you do any atmospheric calibration before data analysis steps?
So, yeah, good question. So we did removed black noise. So this isn't a atmospheric calibration, but took out the black noise signal right away as part of the radiometric correction. And then the actual radiometric correction, where every pixel, and this was a calibration file provided by Resonon, where every pixel was converted from our raw digital number to the radiance value based on the lens, the pixel, the sensor for each pixel, adjusted by the frame rate, the gain and the offset, those sorts of things. So when we had radiance, then the next step was converting to reflectance. And since we use the empirical line method with with reference panels that we placed on the ground, so to answer the question directly, we did not do any atmospheric calibration aside from this assumption that anything that we were imaging from the reflectance panel, since it was on the ground at the same level of the target, which would be the corn plants, there's an inherent atmospheric calibration component in that during the reflectance conversion. And honestly, since we're imaging from a drone, at least a lot of the people I've talked to over the years on this particular topic, it's not a big deal. It's more of a big deal when you're at higher altitudes in a plane, and especially satellite.
Okay. Thank you, Tyler.
Yeah. Okay, yeah, like I said, there's two main functions, and I'm gonna dig right down into each of these. And if you're able to pull up that link that was shared earlier, you can kind of follow along on these. So to set this up, first, just consider these data layers. We have our hyperspectral data cube and our plot boundaries. So this might be a shapefile, it might be a GeoJSON. But we have polygons that represent the plot boundaries with a plot ID for each area. And before I move on, I said I would point out when we see a picture of a hyperspectral image cube. So this is line scanning. So I don't know if this image was captured from east to west or west to east, but the gimbal, you know, when we're going through, there's wind and everything. The gimbal's trying its best, but the camera's kind of always going a little bit back and forth. And so that's why we don't see a straight edge, because every line is actually being reprojected during the geo-rectification process. Not reprojected, projected onto a coordinate reference system. And so this is being done, you know, the IMU is collecting data every 5 milliseconds. And so we're just matching up the timestamps. And so that's kind of the result that we see. With that said, it was always my goal to get a perfectly straight line. Okay, so back to, you know, considering that we have both this data cube and our plot boundaries, you know, when I asked the audience, you know, does this look familiar? Like, okay, what now? We have some number of plots in here that we want to do analysis on. So what should we do now? So my goal has always been, okay, let's crop this image by one of the plot boundaries so that we have a more manageable image, so that we don't have this big hyperspectral data cube that we don't even know really, you know, using the image itself. We don't know which pixels in there we want to use for analysis. You know, this question, where does one plot end and the next one start? So when we load them into our GIS, we see, okay, they overlay really nicely. There's a question about how accurate was that geo-rectification process, which I will touch on a little bit later on. But for now, let's just assume that this is perfect. Let's focus on plot 917. So our goal here is to crop this large hyperspectral image that contains all of these plots by the plot boundaries of 917. So I'm gonna now go through the demo of this crop single function, and just before showing the code, that's the Python code needed to do that. I want to just show this slide right here that let's see. I guess because of how crop single behaves, this function crop single, and because of how crop many GDF behaves, they kind of can work together when you're trying to plot many of these plots. So crop single is more basic. I'd say less user friendly, but I'm going to start this demo in this less user friendly format here. So to do this cropping, crop single wants to know the origin for which to crop. So the origin being the northwest, and if you're looking on a GIS, the upper left corner of where you want to start cropping from, and it wants this to be in units of pixels. So I have this whole hyperspectral image. Let's zoom in right there, and I can decipher where the different pixels are. So I can click, this was done in Spectranon, click a particular pixel, and I see that my northwest origin is that I want to use is the 342nd column. So going east and west, and the 75th row going north and south. And so let's just consider that, or keep that in mind, jot that down. And also we're going to crop an area that's going to be 200 pixels in the eastern direction and 50 pixels in the northern direction, actually going south. Okay, so here's our image. This is just the file name for where I have this stored on my computer locally. And getting into some of the Python code, which you'll be able to see in that Jupyter notebook from the link that was shared. First, we want to load and initialize both the HSIO and the Spatial Mod modules. And again, HSIO is all about data reading and writing and then manipulating the metadata. And the Spatial Mod is doing the actual cropping. So we're going to load in our file name and then pass that to our HSIO class. And then we finally pass this instance of HSIO, actually the spectral file, to Spatial Mod. So this is just initializing everything to do what's next. And so now thinking back to last slide, we wanted to crop this area, which we just defined the parameters. So now we just, in Python, just pass those parameters to the spatial mod.crop single function. So our origin pixel in the eastern and the northern direction, and then what the extent or how big we want to crop this particular image. In our case, 200 pixels by 50 pixels. And it returns a NumPy array and the metadata. And these are in a format that I mentioned earlier. Spectral Python is what this HSIO class is really based on. So these are in a format that Spectral Python then can go and write back to file to get our the hyperspectral image file. And then finally, in this case, just save to file. In this case, I'm just writing it as a 3-band TIFF. There's obviously functionality to write to the data cube as well. And so, I guess I maybe didn't mention this yet, but this 342nd column in the 75th row, this corresponds with that plot 917 that we're trying to plot out. And yes, this is very annoying. This is a manual process, but I'm just demoing how crop single works. And it's kind of, it works in the background in some ways to the more interesting or the more usable function, which is crop mini GDF. So when I pull this in to my GIS, I'm just looking at the dark is the full hyperspectral, and then this brighter area is what I actually just cropped. And so it did what I told it to do. Here was my origin, 200 pixels wide, 50 pixels to the south, and it worked. But like I said, it's far from ideal because now what do I do? Do this for all of my plots, and think back. I've got my shape file or my plot boundary file anyways. Like, how about leverage the data that's in there to do this more automatically? And so, yeah, I'll get into that. But before I get into that, I'm going to dig into the different arguments that crop single takes. And the reason I want to do this is just to demonstrate the flexibility of HS process. And really, I think it addresses a lot of different issues that we see when trying to crop imagery related to errors that might be GPS errors, or we want flexibility over, exactly what we're cropping out. So I'll go through these. So first, I already kind of showed this. So pix EUL corresponds to the upper left pixel column, so the eastern direction, to begin our cropping, so the origin. And then the same goes for this pix NUL, but just in the other direction. And now there are some other parameters here, some other arguments. So the crop ePix, this corresponds to the number of pixels in each row of the cropped image, and then the number of pixels in each column. And so I had already gone over that. And now I want to show now that, okay, so far we're just dealing in pixels here, the number of pixels, but a lot of time, like, okay, we want to generalize this. We don't necessarily care how many pixels it is. We only care about how long it is in map units. So for this argument, so the crop E argument, there we have the choice: are we going to pass it units of pixels or pass it in map units? In my case, meters, because I was using a UTM projection. So same thing, only instead of pixels, it's the length of each row of the cropped image in map units. And so in my case, for this example, I could have passed crop EM equals 8 and crop NM equals 2, and we would have gotten the same result. So the user has the choice on which to work in. Okay, now I'm going to get into the taxonomy of this to try to avoid any confusion, hopefully, or clear up any confusion about a lot of these different arguments. And so there's a dozen arguments that look like this, and they follow this taxonomy: type underscore direction underscore unit. So going to our example, crop underscore N underscore M, this is the type is crop, and I'll get into that in just a bit. The direction, this is the northern direction, as opposed to if it had an E, it'd be in the eastern direction. And the unit, either pixels or map units, M or pix. And so what are the different types? So we have crop, we have buffer, and we have shift. And I'll explain exactly what each of these are. Two directions, both northern and eastern, and two different units, pix or M. So the user of this library can use any combination of a type, a direction, or a unit, and then that makes up that particular argument. So what do these different types mean? So crop is simply the size of the cropped image. And here are the four options: either the eastern direction or the northern direction, and either meters or pixels. The second type is buffer. So the buff syntax. This is the buffer distance to be applied after considering crop. So a positive buff will actually reduce the size of our cropped image, and a negative buff increases the size of our cropped image. So for example, if we had, say, crop E pixels, so the width of our cropped image was going to be 200 pixels, we can set buff E pix to be, say 50. And that's going to say it's going to cut off 50 pixels on either end in the eastern direction. So now instead of a 200, instead of an image that's cropped at 200 pixels wide, it's going to be cropped to 100 pixels wide. So this setting, this feature, gives us the flexibility to take our shapefile, that is just the plot boundaries, and manipulate or set exactly how we want that plot to be cropped. In my case, I oftentimes had 4 corner rows in a plot, or 6 or 8 corner rows in a plot, and I only took my ground truth samples from a single row. And so I oftentimes wanted to, like, my scale of sampling was just in that row. When I'm doing my machine learning modeling, I only want to grab out the pixels that were, I guess, that represent the actual plants that I measured. I mean, in an ideal world, we have perfect uniformity across this whole plot, but especially with nitrogen management, we see that there's a lot of variability, and I just wanted to try to remove that variability as much as possible. This argument allowed me to do that and do exactly what I wanted to do. And finally, this other type, GDF shift. This is the distance to shift the cropped image. And again, this is applied both after the crop steps and applied after any buffering. So this is just a shift in the case when the GPS or the inherent geo-registration of our image is actually off from where the plot actually is. And I'll show an example of this in a few slides here. So a positive GDF shift shifts the image to the east or the north, depending on which argument it is, and a negative shifts it to the west or the south. This is only relevant when we pass our plot boundary file, the shape file or whatever. Yeah, and like I said, ideally we would never have to use GDS shift. If we lived in a perfect world, and maybe with RTK capabilities, we wouldn't have to. We did not have RTK capabilities on our drone and our system. So GPS and IMU accuracy are rarely perfect, and we can see that pretty clearly a lot of times when we overlay our image or overlay our plot boundary on our image. We see that it's off, and this is an example of that. So this is a hyperspectral image that I had placed. So we collected this image. This is a cornfield right around V5 or V6. And I had placed a blue bucket lid, from like a 5-gallon pail, a blue bucket lid in the northwest corner of plot 108. Plot 108 is, one of the plots that I was going to sample on this particular day. And so I found that this is very helpful if I just go and put bucket lids out at the beginning of the season. When it comes time to do the processing of the imagery, it really helps to be able to know or have like some of these ground control points where I know exactly how to relate the plot boundaries to the images that I see. In this case, the IMU and the GPS accuracy of our system during the geo-rectification process done by Spectranon, it placed the image 2.76 meters to the west and 2.79 meters to the north of where it should have been. And so these plot boundaries were created with RTK GPS, and so they're considered to be the gold standard, the truth. And so this GDF shift argument allows us to just, after the cropping, after the buffering, if we, it'll actually shift the image. So then from here on out, any steps after that are placed properly in plot 108 where they should be placed. Okay, so going back to our example, we're going to crop the image by each of the plot boundaries. Okay, so we introduce this GeoJSON plot boundary file. And again, load our modules. The only thing different from the last time is now we're loading our plot boundary using GeoPandas. And we're initializing the instance of Spatial Mod, passing the SPY file, and then also giving some information of some of the base directory that our image is in, and then some other naming parameters, which I'm just not going to get into today, but it just helps organize the particular files. And then finally, I use this crop many GDF functions, or this crop many GDF Python function. And this, it takes in both as arguments, it takes in both the hyperspectral image and our plot boundary. And it doesn't actually do any cropping. It returns a data frame, a pandas data frame, to describe exactly how each of the plots should be cropped. So in this case, I had, 40 or so plots that were in this particular image. And I got back this data frame that says some of the file path or where the image exists. And then all of these different arguments are the column headings. You'll notice a lot of them are null, meaning that, okay, they're just going to be ignored for now. But it populates all of the required arguments to pass to the crop single function to actually do the cropping. And so we have a plot ID. So whatever the plot ID was in our field bound or a plot boundary file, that's pulling from there. It's identifying the origin pixel to crop from for each of these plots. And then based on the size of the polygons in that GeoJSON, it's defining how big to crop that image in units of pixels. And then the next step is just to go through using a for loop to call crop single and then do the cropping and then write or save the crop data cube to the file. So instead of looking at the nuances of the code, you can do that on the GitHub page or the documentation. But in this for loop, the first thing we do is read the cube based on that file information in that df plots data frame. Step 2 was to call crop single and actually crop each cube. And I do want to point out here that in this example, I snuck this buff easting meters and buff northing meters arguments in. So I'm going to be doing an additional step here that at this point that is just being introduced now. So I'm going to, after doing the cropping, I'm going to buffer in the easting direction by 2 meters. And then I'm going to buffer in the northern direction by 0.75 meters. The idea here is very common, is to just reduce the edge effect that we see oftentimes in the edge of the plots. And then finally, save each cropped image as its own file. We're saving both as a GeoTIFF, a 3-band GeoTIFF, which is nice for loading into GIS program, as well as writing the full hyperspectral data cube. And that's it. We ran that for loop, and now I have all of these cropped images. They're each separate files that when I load them into my GIS program, they show up exactly where they need to be. And you notice that buffer step. So yeah, we buffered 2 meters in the eastern direction and 0.75 meters in the northern direction, and that shows up here. And this is how it compares to the raw or the original hyperspectral, the full data cube. The cropped images are a bit brighter. So I ask this question to myself often through this process of developing, especially, like, is this all going to be worth it? But in hindsight now, I can ask, was it all worth it? And it's a pretty easy answer for me because, like, okay, would I rather have something like this? And what I'm showing here are just the file paths of the original hyperspectral images, or something like this. And these are all of my cropped images. So first, focusing in on the file names. These are really long names. As we just saw, there's a lot of plots within each image. I have no idea what's going on there. Over here, I have the study, the date, and the plot of each image. And so they're nice and organized. I can do my inventory nice and easily. Focusing in on the size of these files, we're talking close to a gigabyte for each of these. Not very manageable. They're not uniform. Over here, they're 20 megabyte files, and they're all consistent because they're all exactly the same size, which was ideal for my workflow. Now, looking at this from more of a spatial perspective, we can ask the same question: would we rather have this when we're starting our analysis, or this, where each of our cropped images is lying exactly in our plot that we have? And in this case, this was an example where I extracted out just a single corn row the exact row that I took my ground truth sample from.
Hi, Tyler. There are 2 questions. Do you want to take them?
Yep, absolutely.
Okay, so the first one is, I ran into an error when running block 4 code. Map information was not able to be loaded from the SPI file. Please be sure the metadata contains the map info tag with accurate geometric information. I guess this is the error that he or she found.
Okay, interesting. So no map info. The sample data set should have been georeferenced. And I wonder if the file path is, maybe there's an image that was not georeferenced and an image that is georeferenced. And the first place I would look there is just to see if you're calling the wrong image.
Okay.
But you can look at the header file to know explicitly, is map info a metadata tag? If it's not, then we have to find an image that's georeferenced. If it is in there, okay, then we got other issues that I'll have to look into.
Okay.
But yeah, feel free to follow up with me.
Yeah.
Afterwards, like if you're trying to work through this, and we'll definitely get those sorted out.
Yeah, we can also link your website in the comments so people have all the information to reach out to you. The second question is from Michelle. So can you comment how accurate is the PCAS second GPS IMU unit and Geo-Rectification Module of Spectrum Pro? I can see lots of distortion in your processed imagery.
Yeah, absolutely. So first, focusing on the GPS and the IMU, the projection of the raw pixel data to a coordinate reference system. The accuracy was often within 3 to 4 meters, give or take just a little bit. Rarely within 2 meter accuracy, which is oftentimes a problem with small plots when our plots are only 1 or 2 meters wide in the first place. And so that's why this GDF shift parameter argument was introduced, so we could kind of correct that at this point. So that's from the GPS IMU perspective. So like some of that it's hard to decipher. Some of that might have been because of I say poor, but like error in the GPS accuracy. Some of it might be error from the IMU. And because they're kind of working together without only using the data I have, it's impossible to decipher which is the culprit there. Now the Geo-Rectification Module of Spectranon, that's only using, well, there are different settings, to say how to do resampling and things like that. But it's more or less just taking the data from the GPS IMU and projecting it onto a coordinate reference system. In my processing, I also passed the digital elevation model. So it knew at what elevation above sea level the land or the field that I was flying over, it had that knowledge, which was accurate to, it was a digital elevation model accurate to, I think, 10 centimeters or so. With that said, the GPS altitude is not usually very accurate. I want to say ours is accurate to 5 meters or so. Usually it's within that, but it's really hard to say. Now, the last comment, I can see a lot of distortion in the processed imagery. Yes, absolutely. And there's different ways you can look at that. Sometimes it's the image itself kind of showing these wavy patterns. A lot of times that's just due to the wind. And the reason that it's showing wavy is because the Geo-Rectification tool is just taking the IMU information and projecting it onto our coordinate reference system. And the other place to look is when zooming in. If I can, yeah, It's kind of fuzzy here, but like when we really zoom into a plant, yeah, it is a line scanning camera. And so it's like a video camera that we're moving over space to provide a static image. And so it's not the same as a two-dimensional image array that you see with multispectral cameras or RGB cameras, like from your phone, where it's capturing all these pixels at the same time over space. One hyperspectral image cube, it took us 20 seconds to collect. And so we're flying that drone over that plot. And so there's wind that's moving the leaves. The camera itself is moving. The drone is moving. There's wind moving the drone. And so all those things kind of cause blurry imagery, the look of blurry imagery. And in our research, the idea that we have hyperspectral data, it overrides that negative part of having some of that wavy imagery. So yeah, hyperspectral imagery from a line scanning camera, don't expect to have great spatial characteristics, but what we get is the spectral dimension.
Okay, thank you, Tyler. And Jeff for the question.
Okay. So a quick summary of this cropping tool. And some of these are my opinions, I suppose, but I certainly look at them as benefits, especially, in looking at how you want your whole pipeline to behave and trying to automate everything through. The first benefit, we have smaller images. Not only are, they're more convenient to handle, smaller data size. Like when we're doing visualization, it's really nice to not have to load in a 600 or 700 or 800 megabyte image just to take a look at it. It's nice to just load in exactly what we want. This uniform image size, and what I mean here is just similar pixel number. The reason this was a benefit for me is because if you remember back to the slide where I showed the segmentation step, I took the 90th percentile of the MCury2 index and I removed all the pixels before that. I only kept above the 10th percentile. And when having images that are different pixel number, now we're introducing a bias possibly in how we're doing some of these downstream steps. And so having a uniform pixel number within an experiment, we're able to compare more apples to apples when doing processing or analysis that looks at the distribution of the pixel values within the image. Thirdly, as you briefly saw from that screenshot, the HS process is putting the location or the study, the date, and the plot ID saved all in the file name. So not only does it you have transparency into your data inventory. What data do we have? What data are we possibly missing? But it allows for this one-to-one join with other data points, the ground truth samples. In my case, we collected whole plant biomass and whole plant. We sent that in to get nitrogen concentration for each plot. And so now I crop this in a way where I have a one-to-one join with each image to each ground truth sample. And then another benefit, spatial integrity is not only retained, like we still can load these into GIS and they show up exactly where they belong in space. Not only is the spatial integrity retained, but with the GDF shift argument, we can actually improve that past, when we have GPS inaccuracies or whatever, we can shift that. And at this step, if we want to, it's a little bit of an extra effort, but we can put that image exactly where it belongs. So everything downstream, we're working with accurate data. This is important for spatial analysis, and then of course for geospatial visualization. And the biggest benefit for me, every downstream processing and analysis task from here on out can be 100% automated. I don't have to, you can, it's a lot easier to just write a script or whatever when all of your inputs are consistent with one another. And that's what this does. now before moving on, I want to just address probably a question that maybe some of you have, and that is, was HS process necessary to achieve all of these things? And the answer is, absolutely no. Like, this could have all been done manually, for sure, using a point and click type of a software. But if I did my master's program project that way back in 2011, 2012. And I spent weeks and weeks doing this. And then a month or two later, I wanted to change one of the earlier processing steps. And then I redid it all. And that is the big reason that, okay, yes, all of this can be achieved manually, or even with other software, sure. But the idea that while going through this, we can script out for our particular project, for our particular data set, if we ever need to come back to it a week from now, a month from now, maybe 10 years from now, we can take that script and just maybe change some parameters in changing how we're going to do it, and in a matter of a minute, depending on our data size, in a matter of a minute or an hour or a day, everything is just done without having to go through the tedious parts of the point and click UI software. So I'm going to pause there just for a bit, and first ask, any questions at this point, how we're doing for time. I see it's almost 1 o'clock.
Hi, Tyler. Yeah, so we are almost close to 1. So there are no questions for the moment, one non-additional question. So how long is this part is gonna, because if it's like 15 minutes, we can stay on, but if it's too much, maybe we should cut. It's up to you.
Yeah, well, I'll go through. Yeah, I mean, the remainder, absolutely. It's 10, 15 minutes, I would say. I don't plan on getting into a lot of detail. I just kind of wanted to, I'm showing all this data, and yeah, the focus of this workshop is to show the methods that I employed. That's what I did. But, it's oftentimes back end, okay, what happened? What are the actual results? And so I just wanted to spend a few minutes showing.
Yeah, go ahead. And Felipe, you're muted.
Can you hear me?
Yes, now yes.
Here we go. Yeah, no, it's great. Yeah, go for it.
Yeah, go for it. Like, I guess we can stay for 10, 15 minutes more.
Thank you.
Okay, I will just I'll continue on. And just show some of the results from this work. So you saw this slide earlier. We just finished the processing step. Now let's get into the model training. So just some background on what I did is I had my full data set, 247 observations. So this included 247 images that I brought in, or I calculated the mean spectra for. So there's a representative hyperspectral file for each ground observation. So every nitrogen uptake sample that I collected, split into a training and a test set, reserving the test set to assess the final model performance at the end. For feature selection and hyperparameter tuning, I did a repeated k-fold cross-validation from that training set. For the feature selection process, used the lasso model to perform the feature selection. Hyperparameter tuning, did a grid search, cross-validation technique for the different models that I checked out. And so I just compared, for this project, compare 4 supervised regression models, again, to predict nitrogen uptake. That's my overall goal, though. Lasso, SVM, random forest, and partial least squares regression. So this was done using scikit-learn. So that's a Python library as well. So here are the results. And so we're just showing the predicted nitrogen uptake on the X and what was actually measured then on the Y-axis for each of the different for each of the different models. The colors in here correspond to different pixel sizes. So like I said, earlier, these different experiments that we had different scales of research there. And so we had to fly the drone at different levels. And so I just wanted to really be able to highlight, okay, where, where are there trends for particular pixel sizes? And then the shape of the point shows what the growth stage is of the corn. So as the growth stage progressed, the nitrogen uptake increased. And so I'll just pop the results up here to show. But I just kind of want to give a summary of what these plots show. The range in observed nitrogen uptake, from about 5 to 180 kilograms per hectare. So this was a pretty wide range, which is I get really excited about because it's a fairly robust model. And the range in error from 15 to about 18 kilograms per hectare. The comparison of the different models were pretty similar, with the exception of random forest. It overfit a little bit, so a little bit inferior. So answering this question, can hyperspectral imagery predict early season nitrogen uptake? Yes, with actually very high accuracy. And so we were really excited about that. But we can ask this other question, is hyperspectral imagery useful for making a fertilizer recommendation? Think back, this is what we're, the goal of the research is actually to do. And the answer to that is, probably. In our case, the cost of this equipment is still high. The turnaround time on image capture and processing is less than ideal, although I hope to have improved that, certainly for myself and hopefully for others going forward with HS process. And the real problem here, we're still trying to fertilize during the early season. And a lot of the things that relate to crop nitrogen demand happen later in the season because of things like weather. It's hard, we can't predict weather. And so the research question that came out of this project, we have to understand better the relationship between crop nitrogen uptake and crop nitrogen demand. So be able to predict future nitrogen demand based on trends that we've already seen to really get at improving fertilizer need. And I'll just kind of skim through these. I don't need to show the conclusions of that because I already said it. And then lastly, so that's it for the remote sensing component of this. I just wanted to I mentioned earlier this EONR Python package. This is something that I actually did before HS process, but it's another open source package that I developed. I just want to give just a few minutes overview on what this is for any of the audience members that might be doing nitrogen research or rate response research and might be able to make use of this. So EONR stands for Economic Optimum Nitrogen Rate. The concept is that we want to make the most favorable fertilizer recommendation considering 3 variables. So our grain yield response to nitrogen. So we'll usually put in these experiments where we have different nitrogen rates, and we'll plot yield against those rates, and we'll see something like the blue line here. Yield increases, and then it plateaus at a certain point. And then these other 2 components, the economics, so the grain price and the fertilizer costs. So the fertilizer cost is this green line, and then the red line is just the blue minus the green equals the red. And so we see this plateau or this optimum point, and that is the EONR. And this will change. It'll be a different nitrogen rate will be our optimum depending on the economics. So as grain price increases, as grain price increases or nitrogen fertilizer rate, nitrogen fertilizer cost increases, that point will move around. But that's only a point, and this was calculated using usually a lot of measurements from different plots. And so there's some uncertainty around the EONR, and that's oftentimes, it's not reported, or there's corners cut when reporting it. It's oftentimes reported as just plus or minus $1, which has absolutely no statistical basis. But that's the common trend with this kind of data. Then there's some different methods. This UNR tool actually calculates the uncertainty using all the different methods. And then there's one last component, this social cost of nitrogen. The social cost of nitrogen, getting at this environmental piece. This is defined as the present value of monetary damages caused by an incremental increase in nitrogen. And so there was some research actually done at the University of Minnesota, trying to, quantifying what the cost of nitrogen is spatially across the state of Minnesota. And this is in units of kilogram of nitrogen applied. And so for some of this particulate matter, so ammonia volatilizing into the atmosphere, in the Twin Cities metro, this is valued, maybe $5, $10, up to $50 per kilogram of fertilizer applied. So if these numbers are true, they're very substantial, this social cost of nitrogen. So this UNR package, you can read the documentation, unr.readthedocs.io. It supports both a quadratic and a quadratic plateau model, uses a generalized cost function. What I mean by that is it allows you to introduce this social cost of nitrogen component in the calculation of your optimum nitrogen rate. And it makes it easy to report uncertainty and possible to consider some of these externalities. And hosted on GitHub, just like HS Process. So go ahead and check it out. This work was published in Computers and Electronics and Agriculture. And then finally, some conclusions that C wanted me to share. So the HS Process Python library was developed for processing drone hyperspectral imagery used in small plot and on-farm research. I hope I was able to demonstrate that, and I hope people use it. That's a big question I have: is it going to be useful? I'm certainly interested in continuing development on it, but I will say it makes it a lot easier if there's collaborators, if there's people that are looking to help me do it or collaborate a bit to make it better. So certainly reach out if there's interest in that. Also, the UNR Python library was developed, and the research results were promising. So for C's lab, the future direction, she's planning on widening her research scope, looking at multiple nutrient stressors at a time. So differentiating between nitrogen and sulfur, for example, looking at different things like yield, disease, all using drone hyperspectral imagery. Interested in developing some more standardized protocols for processing drone hyperspectral imagery. I think using HS Process, and then some more long-term downstream effect of the research, a need to reduce the cost of the technology, build more cost-effective multispectral cameras that have only the wave bands or the wavelengths that are important for a particular use. And then compare across different camera brands or spectral configurations is also a research goal. And then just put up here some of the funding sources for this work through my dissertation at the University of Minnesota and my advisors in my committee. And then I also really want to acknowledge just the open source community. So Python and particularly GDAL, Geospatial Data Abstraction Library, GeoPandas, Rasterio. Those are both Python libraries. And then Spectral Python, like I said, like HS Process relies on Spectral Python for all the reading and writing of the hyperspectral data cubes. And so there's a lot of functionality just inherited from this library within HS Process. And then I just wanted to point out Resonon. nothing but good things to say about the Resonon company. Resonon. This was the manufacturer of the hyperspectral camera we used. The customer service was great. Anytime we had a question, and honestly, their hardware is as good or better of anything that I've ever used or had to take data from and process and analyze. So. And then Sentera, they've supported me along, the last several years in doing a lot of this work. And I, C mentioned it in the introduction, but I graduated just a few months ago, and now I'm working for Sentera to help develop digital agriculture products to help turn a lot of this data into real information. And that's all that I have. So thank you, everybody, for your attention. And I hope this is beneficial. I hope it's informative. And I really look forward to having some conversations as follow-up, particularly related to HS process. So,
well, thank you, Tyler. It was like a very interesting and useful workshop.
I'm not able to hear you right now.
Yeah, dude, you did a lot of work, and that was very cool. You have actually material to do more than one workshop, though.
Yes.
I can't hear you either, Felipe.
Oh, I'm mute?
Sure if
there
are the problem.
There are two questions if you want to take them. Do you hear us?
No? Can you hear us?
Oh, no, I think he doesn't hear us.
Okay.
I don't know why. Do you hear me, Felipe?
Yes.
Okay.
People there watching us can hear us. Say yes. Type yes.
Oh, maybe I will put him. Do you hear us, Tyler?
Can you hear us, Tyler? That's quite interesting.
Yes, there are many yes. So I think.
Okay.
But
can you hear me?
Yes.
Yes, we can. Can you hear? What about you send us questions in the chat private?
Yes,
chat.
but we can hear. So
Yeah, guys, you are over there watching us.
Okay, I will ask
others can hear Felipe and Anarita, but there's a couple questions that maybe I can address.
Perfect. He read my mind. Here we go.
So the first one is, hi, Tyler.
Okay, yes.
I'll
answer the question. I can't hear what you're saying, but I'll answer the question. Okay. So question. I saw you specifically named early season nitrogen uptake. What about mid and end of season? What results would you expect? So yes, only early season before tasseling. We actually collected data up to V14 corn growth stage. The reason we focused our research there was because, we're trying to make management intervention or make a nitrogen fertilizer recommendation. And usually by the time the corn gets so tall, there's a lot of logistical challenges around getting that nitrogen applied. And then also there's that plot that C had showed early on, nitrogen, the uptake rate of nitrogen. By the time it gets to be mid or late season, we're either at that peak or past that. And so it's too late to put on fertilizer and get a response from it. But to your question, what would you expect the results to be? Honestly, I think the results from a relative error perspective I would expect them to be similar. From an absolute perspective, units of kilograms of nitrogen uptake per hectare, I see that widening out just because now we're dealing with a lot more biomass. And then another thing also that would contribute to that higher absolute error that I would predict at those later stages is that early season, with this hyperspectral imagery, we're able to segment out the soil and only analyze the pixels that represent the actual plant itself. And so I think that is and then we did some other things that I didn't touch on today on that segmentation step that you can see in one of the publications. That really, adds another feature other than the spectral information to try to get at more of that biomass component and add it in as a feature, which actually improved the results about 15% from our error rates. So that was really good. So that's that question. I see another question. Can you use your hyperspectral data to make a multispectral to do this nitrogen prediction? Did you find a limited number of bands that allowed prediction? So yes, this is a good question, and really gets my head, the gears turning in my head on like what's next, or what's coming down the line. So one of the things that I have not done yet, but we collected data in 2020 and some in 2021 on, is we collected hyperspectral imagery and multispectral imagery on the same days with ground truth samples. And I'm sure there's I'm guessing there's probably a lot of data sets where we have both, two different camera sensors collect on the same day. But my research question for this is like, okay, can we collect the hyperspectral data? And it's very tedious to collect, but it's so informative. We can do our feature selection, choose among 240 bands, and then we can also like take that hyperspectral data and look at the specifications of a multispectral camera configuration, and then mimic using the hyperspectral data set, mimic what the multispectra result would have been. So a research question that I have is like, can we do this spectral mimicking with hyperspectral data, train the model, and let that data more or less live in history? It takes a season to collect this agricultural data, and there's always new multispectral sensors being developed. And it would be nice when the next multispectral camera comes out, or one that has the particular filters that we want for our particular problem. Well, it would be nice if we had some data to train a model so we can hit the ground running with our new sensor to give us predictions. And so the particular question is, can we do that hyperspectral mimicking, train the model on the hyperspectral data set, but then make predictions on the multispectral data set? What is our loss in accuracy in doing that? I haven't done that yet. We've collected some data, so maybe it's something to come out of our lab in the future here. The other question, did you find a limited number of bands? Yes, we did the feature selection, and out of the 210 bands we considered, the accuracy usually plateaued right around 15 to 25 bands, where we didn't really have any improvement after that. So, and 80% of that was the first 8 or 10 bands. And they were mostly for our project, mostly in the red edge, near infrared, and green regions. And surprisingly, because we had narrowband imagery, we had 2 nanometer differences, the feature selection algorithm oftentimes pulled out bands that were right next to each other, especially in that red edge region. Given some indication that slope or that derivative reflectance is an important feature, rather than just the raw reflectance itself, but like comparing the 2 different features that are right next to each other in the spectral domain.
Well,
okay, I don't see any other questions at this point, and I still cannot hear you guys, and it sounds like others are having the same problems. So I will, I'll just try to help you guys out and draw this webinar to a close. Be sure to check out the YouTube and share the link with others. And I'd like to thank you for the invitation. Really enjoy this opportunity, and kudos to the organizers for promoting this open source software.
Okay, thank you so much. Bye.
Anarita saying something, but I couldn't read her lips. But yeah, thank you guys for promoting this open source software. I think it's very important, and I think it's something that will better science. So
Thank you.
okay,
Thank you so much, Tyler.
Thank you guys.
Thank you.
Thank you everybody for attending.
Well, it was a very great workshop, right? So thank you, Guy. Thank you, Tyler, for please visit his webpage and like all the links that he provided. And I'm sure he will be very happy to assist you if you have any problem or you want to collaborate with him. This is why we are here. PhenomeForce is also this. And so we want to advertise the last workshop of this series, right, Felipe? Do you want to do it?
Exactly. Yeah. Can you hear me?
Yeah, we can hear you. I can hear
Oh,
you.
perfect. Yeah. So the next workshop's gonna be on next week, Friday, on the right time, actually 10 a.m. I apologize for today. We were not expecting so many very interesting challenges to overcross. But yeah, so come next week at 10 a.m. Central Time, we're gonna have a UAV pipeline for image and data analysis using R tools. It's gonna be presented by Alper from Texas A&M University. He's great, and we hope to see you guys here.
Yeah.
And what else, Anna?
Well, there is one last slide where we want to conclude and say that you guys can always follow us and know what we are going to do on our website, that we have a Slack channel. So if you want to join us, you can send an email to phenomeforce@gmail.com, and so you can be part of the community. And we want also to say that soon we will advertise that we will do a workshop in person. Well, it will be most likely an hybrid workshop in person and online for the next MPPN conference in February. So follow us to have more details. And
we're gonna be posting soon in our social media about this workshop at NAPPN in Georgia, February. Yeah, is this? Yeah. So thank you for coming today.
Have a nice weekend and see you next week. Bye-bye.
Bye-bye.